All right, so welcome everyone to the Color Research Society of Canada, our Kaleidoscope lecture series. We're very excited to welcome Jayanne English here this evening or this afternoon, depending on where you are. I would like to begin with our land acknowledgement. The Color Research Society of Canada's activities related to sharing color knowledge take place across Canada, understood as part of Turtle Island, the ancestral homelands of over 630 First Nation communities, representing more than 50 Indigenous nations and languages. We work to respect, affirm, and support where necessary the inherent treaty rights of all Indigenous peoples across these lands and waters. Our commitment to honoring the knowledge, ways of knowing, and wisdom of Turtle Island's Indigenous peoples aims to contribute to the decolonizing work required today for moving towards a just society. So welcome again. We are the Color Research Society of Canada. We're the Canadian arm of the International Color Association, and we host regular talks like this about 5 or 6 times a year. This is our Kaleidoscope series. We also have some members' nights as well. And one thing that if you know any students who work in color, we have an annual student award. So I will put our website up in the chat in a minute, but March 1st is the deadline. We have undergraduate and graduate awards. If anyone's working in color research or color practice, artists, scientists, linguists, and anything where color plays a role, we offer our student awards. So if you know any students, please let them know. If you're a student, think about applying. I'm very happy to welcome Dr. Jayanne English. Jayanne and I have known each other for a very long time. We were undergraduates at U of T a very long time ago, and cultivated a friendship because we both have this dual interest in art and science. And I went to England and Mexico, and Jayanne went to Australia and Hubble Space Telescope, and I'm very excited to hear about her work. She is a senior scholar in the Department of Physics and Astronomy at the University of Manitoba, where she investigates galaxy structure and kinematics, how galaxies evolve, and does scientific visualization. She was awarded the 2021 Quillac Award for Astronomy Communication, Public Education and Outreach by the Canadian Astronomical Society. Although she's renowned for constructing astronomy outreach images for the public, which garner millions of hits on the internet, and she's won awards for that, this award was in part for her engagement with artists and the collaborative works they have produced. She received membership in the Order of Canada 2023 for interfacing artistic literacy and aesthetics with scientific visualization. As an associate professor at the University of Manitoba, she trained the next generation of experts and emphasized links between art and science. She received her PhD in astronomy and astrophysics at the Australian National University. We did some collaborations back then at ANU and at the telescope site outside Canberra, and she got her Bachelor of Science in Physics of Astronomy from the University of Toronto, and she's also a graduate of the Ontario College of Art when it was OCA. So astronomy is this rich visual playground, and Jayanne has made some fantastic images. So we're very excited to hear about her process. So take it away, Jayanne.
Okay, thank you very much, Robin. I will not distract myself by saying a lot of reminiscence of what we've done. Okay, so Cosmos and Canvas, employing color perception in astronomy images, is this talk is a revisit to a talk I gave to the Society a number of years ago. I also want to start with the land acknowledgement. With their treaties, the First Nations and Métis, including the traditional owners of the Treaty 1 lands where I now live and work, generously adopted my Jewish ancestors who are exiled by events in Europe. In the spirit of our aspirations to care for our planet and harmonize its peoples, reconciliation, and tikkun olam, I acknowledge and pay my respects to the Anishinaabe, Cree, Ojibwe, Dakota, Dene, and Métis peoples and their ancestors. Wetaskiwin, Shalom, proceed in peace, Miigwech. Now, uh, there are many motivations for data visualization. In astronomy, we've had cognitive tools as part of our practice forever, started way before photography, pencil and paper, and now we have other cognitive tools as well. So the motivation includes things like um, the vast impacts of visualization. For example, some people will argue there will not have been a shuttle disaster if the proper visuals were shown to the managers. Of course, it's clear if you're in an operating room, you can't have visuals that mislead you because it can be dangerous for the patient. On the right-hand side, we have an image here from the Hubble Space Telescope. There was a shuttle mission to repair the Hubble or update it, and that was canceled. And there was a huge outcry from the public because public outreach, including these visuals, had convinced the public this was the best telescope ever. So that got the head of NASA fired. So that's quite an impact. And also, we have now big data. And to understand what's on in our big data, we need to have humans in the loop for quality control, and the humans need visualization. Now, I'm going to talk about two kinds of visualization that research astronomers do. So, I'm not going to talk about artists doing visualization or amateur astronomers doing visualization. I'm going to focus on the research astronomers. And we make figures for discovery science. That means that we make figures for journals and catalogs. And we have to develop color tables, which we also call schemes, in order to explore parameters in astronomy. And we also are encouraged to make figures for public engagement. So these are called public outreach images, and I'll describe them a little more later. Now, there are many elements to images, such as shape and texture, but there's also symbols or representations. And we could probably all read this graph, that's this diagram that's in the middle here. And I'm using this to point out that the cognitive system is more than the human interfacing with the computer. It includes the people that this human is communicating with, and they communicate with the human. On the right-hand side, we're going kind of in a spectrum here to another limit where we have symbols that are culture-based and they're very obscure. Does anybody know? I can turn off your microphone and tell me, does anyone know what these symbols stand for? They actually make something visual. They make fractals. But the symbols here themselves are obscure, they require learning, and Colin Ware, who wrote the book called Information Visualization, calls them arbitrary. I'll be a little more polite and I'll call them conventions. On the other hand, on the other end of the spectrum, we have perception-based symbols. They're easy to read, they rely on human perception, in other words, on our physiology, and they're sensory. So I want to emphasize these ones. Why? So you're all color people, so you're going to know the answer. You're going to know that color has a great impact on our understanding. But let's do this one anyway. I present this to my science colleagues and it tends to blow their mind. We're going to look at this yellow circle for about 15 seconds. Then we're going to look at this black ring and you'll tell me what color you see. So here we go. 1,000, 2,000, 3,000, 4,000. Stare at it, don't blink. 5,000, 6,000, 7,000, 8,000, 9,000, 9 3/4, 10,000, 11,000, 12,000, 13,000, 14,000, 15,000. Look at this black ring over here. What color do you see? Anybody want to say something?
Purple.
Yeah,
Yes,
purple.
purple or purpley blue, but purple. Okay, so these after images can be used to select color pairs, which are called complementary colors that work with the viewer's physiology. You're going to produce, if you see yellow, you're going to produce purple anyway, so you might as well use purple in your visuals. Uh, The thing I like to point out to my colleagues is that no matter how good their legend is, the information that the person's looking at is not purely intellectual. The understanding that they're getting from this visual is convolved with what the eye-brain system is doing. The
Mhm.
other thing is that color is not physical. No house elf came up here and painted purple, right? It's an emergent property, and more than one physical input is needed to generate the perception of color. Now, bear with me while I show you another optical illusion that you're probably familiar with. Both of these circles are the same size. Which of these circles comes towards you and which falls back? So for most of you, the red circle is going to approach, and artists call this warm. So colors that approach are warm, and those colors that recede are called cool. And we can educate our colleagues on why these illusions happen by referring to the eye-brain system. So we have multiple inputs to the eye-brain system, and they include wavelength, luminance, texture, other things. They pass through a double lens system. And this double lens system, because blue bends more than red bends, the blue circle is going to focus at a different point in the eyeball than the red one. And that probably contributes to why we have red approaching and blue receding. When the information gets to the retina, it's a non-uniform field of view. It's not like a CCD at all. And only differences in luminance are transmitted. And there are different pathways along this optical nerve to the visual cortex. And what happens on these pathways is that they can also be called channels. They pre-process the input into something called feature maps. And there's one map per property. There's a map for shape, a map for color, a map for orientation. So the cortex receives a stack of different maps. It's not a projection screen. So let's look at what we mean by maps. This is kind of an illustration of it. If there are three red parts on this image, then there will be signal in the feature map at those points that mean there's red there. And if there are dark areas, there'll be features in a feature map that are signals where the dark areas are. Tricky one here is orientation. When we have orientation, we've got this line here, but we also have this line in the red triangle and this line in the blue triangle. So we've got different signals in the orientation map. Now we can use the fact that we have these feature maps arriving at our cortex to help us make better graphs. So the graph on the very left, it's very hard to distinguish male from female. And that's because the difference between a square and a circle is that a square is just a rounded off circle. There's not a difference in size. And so this is not going to be very instant that you can recognize this. It's not at a glance. But this one here on the bottom right, they've used different sizes, different symbols, and different colors. So they're using these different feature maps, and that's help us recognize the differences in populations of birds at a glance. Another thing they've done are experiments where they give people this patch of numbers all in black, and they say, please count up the number of zeros. It takes some time and there's mistakes made, but if you change the zeros to red, then you will make fewer mistakes and do it more quickly. So I'm talking here about doing it more at a glance for discovery. And the goals of visualization, I'm going to focus on two here. They are the discovery of trends, and we can call those images exploratory images. And we want to communicate our results, and those can be called explanatory images. In order to make discoveries of trends, like where are those zeros, then we want to have strong distinctions to make those discoveries at a glance. Now, some people worry then that we're biasing the audience, the viewers. But when we're writing a scientific paper, we have sections of that paper that are called discussion and then conclusions. So we actually are presenting a perspective or interpretation in that paper. Well, the same thing with an image. There's no objective image when communicating visually. We have to pick a perspective for communication. So if we use the visual techniques correctly, then we're not going to be biasing the data nor misleading the viewer. And I'm going to show an example where we use it naively and it does mislead the viewer. But first, I just want to point out that Colin Ware's book shows this beautiful diagram that shows you how you can, oh, there's a different point here. And you can use size in this case, but imagine the redundancy if you also used color on that larger size point. Color is one of the strongest pathways in the brain, so let's focus on that. So color tables or color schemes are used in pseudo-color maps, and those are where you have only one parameter, imagine temperature, and for the different values of that parameter, you color different colors. So if it's cold, blue, and if it's warm, red is a typical cultural color scheme. Now, if you look at the grayscale here, it goes from dark through to light. And down here, they've tried to order the colors so they also go dark through light. But a lot of people naively use the rainbow color scheme, which goes dark and then light and then dark and then light and then dark. And if you do that, then you will look at the continental US and you will say, there's a jump in precipitation. That's what this map is about. There's a jump in precipitation halfway through the continent. And it's not true. If you look at the legend, it's smoothly changing in values. There is no jump. And this is caused by the different value of the hues here. So I'm encouraging people not to use a rainbow color map. Also, there's two kinds of visualization. So there's information visualization. These are long descriptions, but information visualization is really about finding relations, and that's scatter plots and graphs. Scientific visualization is about having you look at something that has an inherent geometrical structure. And so that's about maps. And here's an example of a colorized map. And this map is a grayscale of Antarctica, which shows the structure at the shore, for example. And then color is overlaid on it. And you'll notice that if you made this gray, it's probably not going to change in value, but it changes in vividness. So this one uses vividness. So I'd just like to point out that if you are focused on graphs, the same visualization principles apply to both, even though we're going to switch now to discussing scientific visualization. Another challenging color map is a divergent color map. And that's where you put two color maps together thinking that you have a breakpoint or boundary. And the standard ones come to white in the middle, which makes it hard to view against a white sheet of paper or white background that's typically used. And then they go from dark until light. So this kind of color map couldn't be used on top of the map of the Antarctic because it would change the grayscale. But we can use these when we really do want to show a boundary. And I'll give you an example of one that we've developed. So most of you know that analogous harmony is sequential colors on this very handy dandy visualization tool called a color wheel. And you know that complementary colors are across on the color wheel. So before we stared at yellow and we saw purple, they're across from each other in the color wheel. I'm going to pick turquoise and red. I'm going to make the turquoise lighter and the red a bit darker and add a bit of red to the turquoise to get a color like this beside it. And then turquoise to the red to get a color beside that, like this one. And if I do this all correctly, then I'm going to get neutral gray in the middle of my color scheme. But, well, the gray is great because you can distinguish it from the white background, right? These are called compensating tones color schemes. And when you're building this, you actually can't just take numbers and add them together. You have to use your eye because your eye is nonlinear and the monitor is nonlinear, so you just can't add numbers together. How did we used to portray these in our visualization tools? Well, something like this. And so, thinking about the optical illusion I showed before, which part visually is going to come towards you and which part is going to go away? The red pops towards you and the blue pops away. Now I'm going to do my galaxy dance. What I have here is a bunch of gas. It's got one frequency, and when the galaxy rotates, I've got part of the disk coming towards you and part going away. Now, some of you know about the Big Bang, from the Big Bang Theory TV show, Sheldon dressing up as a Doppler shift, and others of you know it from listening to a car go by. So as a car goes by, it comes towards you, it goes ee, and as it goes away, it goes ah. So the frequency shifts, and the same thing happens for light. So as the disk rotates towards you, it gets shifted to E, which is towards the blue end of the spectrum. And the part that's going away, my back elbow, goes ah, which is the red part of the spectrum. So we call this red shift and blue shift. So the legend here is red shift and blue shift. Which part is receding? Physically, the part that's colored red, but it looks like it's approaching you, especially this little piece of gas. This one looks like it's going away, as does this part. So if we change, this is our original color scheme. If we change it to this one, we have blue shift and red shift. We don't lose our legend, but the blue instead pops forward and the red recedes. I made the first image about this in about 1993. And here now you can see this fragment of gas is coming towards us while this one's going away. And you can see the change from red through to blue that gives us the rotation of the disk. So this approach of using human perception supports the intended meaning. Here's a newer version of this galaxy. We have a lot more gas we're detecting. And these are made with the color maps that we've developed in our software or Python codes that's called Cosmos Canvas. And this is my crew here, Mark and Gilles and Nathan. And today we got Peter to join us. So what's been happening is we developed this for the changes, a survey of the sky with the very large array that is in the movie Contact. This one is with the ASCAP telescope, and that's a really new telescope in Australia. But it's moving on to other people. Other people want to use it. And so someone has joined us. Just today we had our meeting, our first meeting on this. He wants to attach it to his, these are called velocity fields, his velocity field analysis software. And so it's going to be used by many people when he does that. So that's very exciting. Now, what else can I do with this velocity field? I can change the values and make a velocity field like this, which if I print it out in gray scale, would just be one solid gray, no variations in the gray, just one solid gray. So they all have the same value. That means I can layer it on top of a grayscale image without making the darks light and the lights dark. And so from an image like this one, I can see there's gas that, well, first I can see the galaxy's rotating because it goes from red to blue on either side. And also there's gas away from the disk of the galaxy vertically. And I can see that's rotating too because there's red on one side and blue on the other. And one of our team, Nathan Degg, he's been doing this for this survey with the Australian telescope ASCAP. And so he has optical images that he's made along with these velocity fields, and you can see the rotation in these galaxies. Another parameter that we use in astronomy is called the spectral index. And there's going to be an exam, so remember this. I'm just joking, but we call it alpha and it's a spectral index. And what it does is it characterizes the slope along this emission here. So what we have is wavelength or frequency, if you prefer that. This is for a galaxy. And this is the amount of radiation from that galaxy. And you can see here we have part that can have a slope that's almost level. We call that flat. And then we can have a part that's very steep and sloped. And the reason that there are these differences is because different processes create the emission. The thermal one is in a plasma where electrons are zooming by protons. The steep one is when there's a magnetic field and the electrons spiral around the magnetic field. We want to know in a galaxy, when we look at an image, where are the magnetic fields and where's the plasma? So we've developed a color scheme where we say in this characterization of the slope, the spectral index, where is it flat and where is it steep? And I've picked a dark cyan for the boundary for where it's flat, and then go in a sequence along the color wheel. So this is an analogous harmony towards plum. And then I pick for steep orange, which is the complement of the cyan, and go down to yellow. So again, a sequential set of colors, so it's analogous. And in between, I do that compensating tones thing. So where does this get me when I look at a galaxy? So we have a catalog. So these are being used in catalogs and in papers. So we have a catalog here, and I'm looking at this edge-on galaxy like this. And right here, I can see plum right away. So I can distinguish instantly that this is flat. And what produces the plasma here? Well, it's the plasma around an active galactic nucleus of the galaxy. And what is that? It's the black hole, a supermassive black hole in the center of a galaxy. So I can pick that out right away. But there's something else I can also pick out. These galaxies are edge on. So when I look away from the disk of the galaxy, vertically, above and below, I can see that the emission gets steeper. The slope of that emission gets steeper, and that's because of the electrons in the magnetic field. So this tells me that magnetic fields extend vertically away from galaxies. And I'm just pointing out we're now using this scheme for different telescopes, not just for our changes projects, but also on a telescope in Europe called LOFAR. And sometimes from our papers, because I've just been showing you figures from professional journals, these images, here's another spectral index one, get transferred into the public domain. So let's talk about the public domain. We have public outreach images, and these are images that are in textbooks all the way through to the internet. And the Hubble Heritage Project, I think, described the goals of these very well. By emphasizing compelling HST images distilled from scientific data, we hope to pique curiosity about our astrophysical understanding of the universe we all inhabit. Okay, so we want to build bridges between astronomers and society. I'm going to again emphasize that I'm talking about images made by astronomers. And we want to pique the interest, but not present all of the knowledge about an object or phenomena. What we want to do is get you to go and look it up after, find out more about it. But the great thing about making public outreach images for the young people is that it gets to be fed back into professional journals. So it will go into their articles, and they haven't spent any extra time away from their thesis in order to make these, because it's going to become part of their thesis. Now, in science, we have a strong culture. We like contour plots. And if we think that the contour plot is very clear, then this image must be really appealing. But the public doesn't think contour plots are appealing. So I try to encourage people to use techniques from visual art to create appealing versions like this one, which doesn't lose any of the science in the image. So what we try to do is encourage people to do is use visual grammar. So the techniques of composition, color harmony, complementary colors, and so on, to create spatial depth, richness, and color and detail to engage people, and to communicate some of the content without a legend because editors strip that legend off. And the public desires that these outreach images are in a kind of representation that's called the Western image tradition. And these are compelling images that seem to mimic nature, and they seem to preserve the form of things as they occur in the world. They seem to provide evidence, and they're convincing. But the data that we use to construct these images is not the same kind of representation. It's logic tradition images. So this is based on logic circuits, is where this definition comes from. Counting rather than picturing machines aggregate masses of data to make statistical arguments for the existence of a particle or effect. Well, each pixel in our charge-coupled device or in our radio receivers is counting photons. So it is a logic tradition image that we get. And additionally, eventually in the logic tradition, pictures become surfaces on which quantitative information was deposited. So a good example are our antenna arrays. We need the Earth to rotate about half of its rotation in order for an image to occur. And we use math, we use algorithms to take the signal from the telescopes and make it into intensity on the sky, and we need to synthesize this over time. Okay, so that's our logic tradition image. Now let's go, what do we do with these to make these public outreach images? Well, we have the electromagnetic spectrum up here, and since you're all into color, I imagine you all know this very well. So I'll just say that we take filters or radio channels, and we take the incoming radiation, and we filter out everything except a specific energy band. And here you can see in the Hubble Space Telescope that we get a lot of data in the ultraviolet and in the infrared, collect very little from what the eye would see. And each of these images looks different. And they're black and white because we use a filter and we just get black and white images. So we have to assign color to these. And what we discover is like this galaxy has old stars in the middle and young stars are forming in a ring around it in the dust. Let's go through making an image. I have 6 different filters here, and they're labeled by their wavelength in nanometers. And you can see that each image looks different. Ones that are looking at a broader range of energy, we call broadband filters up here. And I can start to show you in a moment how we put those together to start making our image. But look down here, these are narrower ranges of energy that are sampled by the filter. This one's oxygen, this one's hydrogen, this one's silicon, and notice how different they all are. Okay, let's put the broadband images together first. So we have these black and white images. Just take any manipulation tool that you like and you assign color to them. So because the infrared's at the red end of the spectrum, even though we don't see it, I color it red. For everything the eye sees, all the different colors, we color it green, and then blue for the ultraviolet. Well, what am I going to do for the other 3 images that I want to combine? So the CIE diagram here is based on experiments on people saying, if you're looking at this wavelength of light, what color do you see? Well, the 502 nanometer is going to fall in the green here, but the other 2, the hydrogen and sulfur, are going to be the same color to the human eye. So instead of coloring it what the eye would see, I recommend incorporating the principles from art and design. Let's try to create some spatial depth here. And I'm going to pick warmer color and cooler colors. And when I put them together, assigned to these, I'm not going to lose this chemical information. Instead, I'm going to get, so if you look at this long enough, you'll get some spatial depth because the green's going to go back because it's cooler, and this star cluster will pop forward. And also notice we ended up with complementary colors. So it's going to be pretty appealing for people to look at, and they won't leave the image right away. But it's not the only way. It's not the only valid way to assign colors. And I use this in workshops and classroom assignments. And here's just a small sample of other valid ways to assign color to the very same data. Okay, so one of the benefits of converting logic tradition images into image tradition representations is that they can lead to both public outreach images and discovery science. Now, if we're looking here at these supernova remnants have magnetic fields, and they're assigned colors. The energy ranges are assigned colors that will add together to give you yellow through red, and the red is actually going to be a lower energy, older supernova remnant. But if you look around this image, you will see yellow dots surrounded by red halos. Well, what is something that's going to have magnetic fields? Remember, I mentioned active galactic nuclei, the supermassive black holes in the center of galaxies. They have jets coming out of them, and the jets have magnetic fields. So one of the president of the International Astronomical Union said, Jayanne, you've built an active galactic nuclei detector. So all of these things are black holes, and this image has detected them. Another thing we can do in the radio is treat it like an optical image and use those different energy bands now. Our instruments have changed, so we have different energy bands, and we can assign color to them in the same way we did to the optical. And we can also take that hydrogen data that I used for the Doppler shift and assign color to it. This is a bit subtle, but it's got many different. So what we have for the radio is stacks of images, just like the stacks of feature maps in your brain, but stacks of black and white images, one at each frequency bin. And we can assign to that color, and we change frequency to velocity. This is kind of a purplish red, meant to make it blue shifted, but also come forward and desaturate here. So what we've got here is a gas ring that's orbiting this galaxy. This optical image here, and then the gas ring from radio telescope, the one in Australia in this case. And it shows that this gas ring is orbiting. What's really cool is in this survey, we didn't go looking for polar rings, as they're called, around galaxies, but it must mean that there are more polar ring galaxies than we estimate from optical telescopes. And that in turn will tell us something about how galaxies evolve. Here is a journal article just to show you this figure from a journal, how it gets sometimes converted into a public outreach image. So if the public looked at our radio data, which is not very resolved here and looks like big blobs, they would say, what's going on? This has got damage to the image. So we only use the radio data from the middle here when we're presenting it to the public. And this object is called an odd radio circle, and it's been seen with a precursor to the square kilometer array that's called the Meerkat telescope array. And that is really sensitive. It's very, well, we don't know what these objects are yet, by the way. We didn't see them at all until Meerkat came online a few years ago. This is just to point out that we have to now do some very fancy techniques like masking in order to put together various data sets from different telescopes. So originally, the Hubble Space Telescope images were only from the Hubble, which made it a bit easy compared to now when we're putting together data from different telescopes. And also to show that you can create quite a bit of dimensionality using that warm-cool contrast. Another thing that the public don't like are vectors. So when we have light, we have it can be described as a wave, and everybody can carry along with me. But if we have the magnetic field is for my thumb, the electric field for my pointing finger, and then this other finger is how that wave travels. Now, you know, I've got this pointing finger pointing up. There's no need for the wave to be going in that orientation. It can be like in this orientation or that orientation. And if you have a bunch of them together, all in the same orientation, we call that polarized. And these vectors represent the polarized light, and that light is polarized by magnetic fields. So we're actually looking at the magnetic field lines here. And that took me a long time to describe, didn't it? So what we do is we use an algorithm called line integral convolution to make these vectors into flow streams. And what we do is we put down a noise field in our computer, and then we put in the polarization data. Now, you can think of it like the noise being like grains of sand at a beach. You're on a beach, and then the vectors are joining together by drawing with a stick in the sand. And what we get is this. So we've got rid of the contours as well by putting in an optical image of a galaxy. And now we have these flow lines showing that the magnetic fields are emanating outside of the galaxy. Here's one that I did, and I assigned two colors. The magnetic field lines within the galaxy are kind of in the plane, horizontal, so I assigned them pink. And the ones that are vertically coming out of the galaxy, I assigned blue. My colleague Jelena Stein has used our newer version of the line integral convolution to create this very lovely image of magnetic field lines coming out of one of the Changes galaxies. Now, if you'd like to see a lot of my public outreach images, you can just go to this website, just go to WordPress and look for Jayanne Cosmos Canvas. And usually when I give a colloquium, I give a workshop, and I've given these workshops to artists, elementary and high school students, and undergraduates, graduate students, postdoctoral fellows, and professors. And that's been providing me with an opportunity to visit different places in the world, like the Netherlands, UK, Germany, Australia, South Africa. I like this one here in South Africa, and Switzerland. And in Switzerland, I was invited to be a guest professor to develop a course called The Art of Scientific Visualization. And the students came to me with one of their projects, which was coloring on redshift for cosmology over here, and said, we want to enter an art show with this. So we did in Zurich, and then it was also shown in Toronto. And you'll notice that I'm not only working with astronomers, but also other scientists on this. Now, our visualization tool that I showed before, we're really working with three-dimensional cubes. So this little animation shows you this stack of images in the three-dimensional cubes. And this is what it looks by, I'm going to call it channel by channel or frequency by frequency, if you like. And what you can do then is work with art. I collaborate also with artists. I've just picked one project. And Emily Gong's question was, can we analyze the kinematics of autonomous vehicles using astronomy tools, the one I just showed, and revisualize the results in traditional painting materials? So I made a mock velocity field. Actually, it's three-dimensional in that tool, but I can collapse it to 2 dimensions and color it in my typical color scheme. And then gave it to, well, I worked together with Emily on this, and we showed it at this amazing museum in Shenzhen, China, during a biennale of urbanism and architecture. And what's interesting about working with artists is you reach a community that you wouldn't expect to reach. Usually when people go, say, on Astronomy Picture of the Day, or when I post my public outreach images, I get 1.5 million views the first day. But those are people who are already interested in astronomy. But here you're reaching out to 10,000 people who may not at all be interested in astronomy. So it's very interesting to work very beneficial also to work with artists. And here's what she did. She took each channel, each image, and she painted with traditional paint on transparent media and made this structure. We made this structure because I helped design, but it's room size. It's very interesting to do. And that kind of brings us to whether we can view our striking outreach images as if they're art. The pros are is that people, these are all like culture theorists and art historians, mention that, well, they look like landscapes or fantasy scapes, and they show the mystery and wonder of existence, and so they promote them as art. But there's other cultural theorists who say, well, there's more than one person making it, and there's lots of software involved, and there's a lot of contrivance. And other people say, well, it's not going to advance aesthetics or critical thought. And I really like James Elkins saying there's no formal connection to concerns in contemporary painting and photography. And that's very true because our intention is just to reach the public. But so I generally say they use techniques from art but are not artworks. But Martin Kent, who is a very renowned art historian, said, so what? It doesn't matter. Visually, they're fascinating and worth studying. And then Ian Carr Harris, who's one of my instructors at the Ontario College of Art, told me the following about this image. To be able to picture for us the complexity of a universe that lies behind that image, an image that is itself not an image, but a pictorial representation of forces we hardly understand, is amazing. We, of course, make convenient distinctions in defining human purpose, but what you have made is, at its most basic structural level, a contribution to the practice of art. So I think I might have to rethink about whether these are art or not. I just want to say that life is moving on for visualization. We have now the square kilometer array, which is global, and it's got telescopes in both South Africa and Australia. That is going to have so much data, and we need to use virtual reality to look at those cubes. So as you can see, when we compress it to the 2 dimensions, take that cube and put it on our monitor, we can misinterpret what's going on in our data. So in South Africa, they're developing virtual reality tools so we can look at our data that way. So I'm looking at some of my data here, but we're also doing some work at the University of Manitoba. And that, of course, was me, my VR headset. I hope I have enough time to go through a bit of a summary here. I've shown you that we have motivation for doing visualizations. They're an important component of a cognitive system, and it's now very important to develop visualizations when we're using computers. And then I described our motivation for using perceptually based symbols and include the eye-brain system when we're making our visualizations, because illusions show that the eye-brain system has a really strong impact on how we perceive the information. And we want to have clearer communication, and we can do that by using our physiology. And so when we're doing information visualization, we can use the channels in the eye-brain system to create at-a-glance communication, which is going to help us make discoveries. And I'll run this little video as I'm giving the scientific visualization and visualization research summary. So color schemes can be designed to aid discovery science, like the active galactic nuclei in the center of galaxies, and it can be used to communicate with the public. And when we're looking at communicating with the public, we started off making those to be explanatory images, but we discovered they were exploratory images as well. So they got us to look at our science and from that develop our new research directions, for example, and make discoveries. So they have fed back into our professional journal publications. And I showed you an example of the research, which is our line integral convolution to show magnetic field lines, and now pointed out that we're going to go on to virtual reality. And I think that's it. So thank you very much for attending my talk.
Thank you so much, Jayanne. That was fantastic.
Oh, thank you.
Lots of claps.
Back to this
Great.
video.
That's a beautiful video. Do you want to stop share? And I'm going to invite
Sure.
people to turn on their cameras if you want to say hi. And I'm very happy to for people to ask questions.
I have a question.
Yes, please.
Okay, what is there's got to be some adaptation by the human user, so he or she knows what this means. If you look at a representation, I look at it, it looks like a pretty color. I have no education as to what to make of that image. What kind of obstacles are there in the creation of these pretty images that ease, or is there quantitative testing of the interaction and the learning curve that is required for a human to actually use these things?
Well, let me go back. I'll just go back to my desktop and go to one of the images. I wanted to focus on colors, so I didn't explain the science so much. But if I look at this image here, oh, I don't know where it's gone. I can tell you, oh, are you there?
Yeah.
I am.
Okay. I can't quit Keynote and I can't see oh, there we go. Can you see my screen?
No.
No.
I need to share screen again.
Okay, let me try that again. But there is information that yeah, entire screen. Let me go to this one of these ones. I guess this one could do, but I do like this one here. Okay, so if I just, you can see in this one, where you can't use one color scheme for everything. That doesn't work. We have too many orders of magnitude. There's too many things to describe. The phenomena are totally different. But what we can do is say the young stars here are colored blue. So these are young star clusters here, right? And a lot of people who have a science background know that hot is actually blue. So when they look at this, they're going to see that that's hot and can represent, so we can represent hot young stars that way. Here is ionized hydrogen gas, and hydrogen glows pink. So this is where the stars are being formed and they're still inside their gas. They haven't blown it away like it has in this tail. One of these things that this image shows is galaxies in a small group. They're actually within the diameter of our Milky Way galaxy. So they're tiny galaxies, very close together, and they feel the gravitational pull of each other. So this is causing all of these distortions here in the galaxies as they feel the gravitational pull. And that's causing actually the stars to form. The gas is falling in and the stars are forming. So as I said about public outreach images, we can't show everything at once, but we can get you to be so engaged with it that you go and explore what this phenomenon is about associated with this group of galaxies. And of course, we always put out information at the same time. So I've started to also write on Astronomy Picture of the Day the blurb that goes with it. So if you look at these on Astronomy Picture of the Day, you get that information. When the images are on the observatory websites, they say which filters are there and what they're colored. And so you get that information. And what's very helpful is like way back when I was a grad student, they cut out a piece from the newspaper of a cosmology satellite, and that had shown the very teeny fluctuations in the black body radiation in the temperature of the galaxy. The cool parts and the hot parts only differ by 1/10,000, but they colored the cool ones cyan and the warm ones fluctuations magenta, and the caption said underneath this image that astronomers have discovered the universe is blue and pink. And that's what we're trying to avoid here by having these kinds of images. And you can see here right off the bat, there's distortions and there's galaxies. So I think we're getting somewhere.
Okay, so sounds fascinating.
Any other questions? Do you want to stop share? We can go back. Yeah. Are you finding that the scientific community is paying more attention to kind of the visual and the way to convey visual information that's more meaningful compared to, when we first, in the mid 90s when it started and everyone was using those rainbow color schemes?
Yes, yes, it's wonderful because I didn't. I spent so much time in the battle that I didn't recognize the landscape was changing, and it's changed totally. So when we started, astronomers thought that they knew better than the artists, and uh, everything was absolutely clear. And now people are coming to me and saying, "Jan, show me how to do this so that it's going to work and people are going to read it correctly." And so and a whole bunch, like, I guess part of the thing that's happened is I did these workshops, which were to students, but the students are now professors, right? Who want their students trained in it too. So the whole thing, the whole landscape about visualization has changed. People are really interested. Partly it's because we now have a name for it. So data visualization makes it sound very official. And so that certainly kind of helps. But people really do want their data to work with the iBrain system. They see the benefits of it. And I think also with the Hubble Heritage Project, we made the images. Some astronomers were signing a petition to stop us from making those some of the images or some of the material, the mosaics that went along with the images. They thought yeah, I don't know. And they went to other astronomers to sign the petition. And one of the astronomers told me, she said, they came to me to sign this petition, but since you made my image, I saw all of these things I had never seen before in my data. And so I wouldn't sign that petition because now I'm changing my research to go in the direction of what I saw in the image that you made for me. So I think they really saw the benefits, and they also know the impact when they're writing their proposals for using telescopes or getting grants. So yeah, it's just changed. Everybody's very interested in it now. Great. It's kind of like the new computer science when nobody knew what computer science was. So it could develop in that direction. I'm not sure if it'll be that impactful, but it feels quite similar.
There's a question by Pat. Do you have a favorite image?
Generally the one that I just struggled with. But no, I have a few. I didn't show one of my favorite images. It's the gas in the Milky Way galaxy. I was very tempted to put it in today, but I knew I was going to run out of time, so I didn't. But the gas is colored on velocity. And so it shows the blue shift and the red shift. And we're embedded in the Milky Way galaxy. We're sitting in the midplane of the Milky Way galaxy. But the color changes across it. So it shows the rotation of our Milky Way galaxy. And it's one of the earliest radio astronomy images that I made. And it's totally abstract. And I love it because I got really tired of making round nebula images and planetary, sorry, Robin, planetary nebulae. That Robin studies are like round and everything was accessible because it had a shape people understood. And I loved making these kind of messy things, right? So I think those are amongst my favorite. Amongst people's favorite are the one that I showed that was the black hole detector and the vertical pink and blue magnetic field lines. Those are among people's favorites.
Question from Alexandra. Is there a difference or advantage to how all different softwares process data, such as PixInsight and Photoshop, or do you
So
use different ones?
I don't use any of the amateur software, and I don't use Photoshop because I train people, and so I can't ask them to subscribe to software. They don't have the money, right? So we use GIMP, GNU Image Manipulation Package, which is free. And I've used that right from the beginning when we were at Hubble Space Telescope because at the time, Photoshop only let you do one undo and GIMP let you do many undos. So if you made a mistake, you were okay with GIMP. So that's where we started with GIMP. And then I have talked, for example, to the people now at the Space Telescope Science Institute. Joe is the main visualizer, Joseph de Pasquale. And for one of the images that I did, uh, they asked me to do this image. It was from, I generally work from our collaborations, and a collaborator had gotten space telescope data and they asked him for an image. So NASA asked me to do this image and it's very noisy. The data had all of this background noise like snow on on a television set. And so I had to eliminate that. And in the end, it turned out doing it in GIMP was better than what Joe was using. So that's so I do find differences, but it's also what you get used to, I must say. So Joe was going, you did a better job than me so, using GIMP. So that was so I'll stick with GIMP. Yeah. Good question.
Great. Yeah, any other comments, questions? If
Welcome,
you want
Alex.
to just unmute and say hello, that's good, or turn on your camera, that's good too. Sarah, do you have any comments, or Sarah's on our board?
No, just thank you so much for the talk. It's really, really interesting. I'm coming from a purely art background, so the science is a steep ramp for me. But the work that you're doing with color and making these extraordinary images available to people is pretty exceptional. So thank you very much.
Thank you for your kind words. Thanks.
Thanks. I found it very interesting.
Thanks.
I did too. It was fascinating. Thank you.
Oh, you're welcome. Thank you.
You're gonna hear my
Good.
dog snore very loudly. Sorry. So I'm an art teacher. I have a background a little bit as a data visualization research assistant. So I worked a bit with Bill Leeming from OCAD on some medical genetics visualization, and I took the science of color at OCAD and learned and astronomy for artists. So I have a little bit of a knowledge of that. I'm now an art teacher, a private art teacher, and I have students going off to university. I have a really talented young student who's an excellent painter and already an astronomy sort of leader really in his groups, and he's done paintings of Hubble's images and had shows. But he's determined he's not going to be an artist and study art. He's going to go and he's going to study science, and it's hard to where do I send these students to see the work that's being done in art and science collaborations?
Um, okay, so there is a visualization group of people in that who do this. So when I started, I could name all five people who did this. And really, it is kind of an addendum to being an astronomer. So I get to slip it into my service work, which is 20% of my contract, but I have other service work to do along with it. And now, because it's figures and papers, it can slip into part of my research component as well. So the student should, first of all, go into science and become an astronomer and keep this rolling as they go along. But there are more options for eventually switching out and focusing more on public outreach now. So, big observatories have public outreach people, and even universities like CFA at Harvard has at least one outreach person. So if that becomes their passion in the end, they can slip out into that. But they're really, again, it's, I don't know how many people is in the visualization group that gets some email and listens to each other's talks and stuff. That's, would be max 50 around the world, right? So you can't take it as a career stream, but you can keep it going when you're becoming an astronomer. If you be, yeah, becoming an, I think that the visualization information is being embedded, as I said, into some of our tools. So one will become knowledgeable about that. If they want to really focus on that sort of thing, if they became a computational scientist, then they could go to Swinburne University in Melbourne and maybe do some of the work there. Um, if I think, I'll tell Robin if I think of anything particular that an entry-level student can do um, to, yeah, it's an idea, actually. Maybe we should have visualization conferences for students. That might be fun.
It's just they're both such strong passions for him. And it would be wonderful to see him, marrying those things and truly being invested in his work from all sides of his interests.
Yeah.
He used to take 3 or 4 classes with me a week. And then, in between his studies. So just a high achiever in both areas.
Well, Robin and I didn't give up either, right? So we kept doing art while we did science. I ran workshops in art, curated in art. I just kept art going at the same time as I was doing my astronomy career. And Robin did the same thing. She'd go off and paint for months in France or something. So while we were doing astronomy, right? So Robin also did this. I did mine in sequence where I did my art college, then I went to do astronomy, whereas Robin was doing astronomy and taking art courses every year, but she didn't do the year, like she didn't do all first year courses. She skipped ahead. If she was in second year, she did second year art courses. So you can just keep, you can somehow find a way to keep it in parallel. It will come together 10 years later, but it'll come together. No, actually 5 years later, after when you get into graduate school, it'll come together.
Yeah, and there's lots of areas, not just astronomy, but you had some images from CERN and particle physics, medical imaging. Like there's all kinds of need now for visualizing data. So the visual skills to play, come into play lots of different places. So we are recording. I'll post the recording. If you want Jayanne's website, if you go to the CRSC page where you registered, her contact information or her website is there. Or you can just Google her name and find it. And yeah, very happy to have Jayanne. Please give another hand. Thank you so much. Lovely always to see you. And I think this place where art and science meet, like for me, color is where it all meets. So art, science, humanities, life in general color just plays such an important role in our lives. So we have to recognize that and bring it into context. And very happy to, blend this with astronomy, which is this other beautiful world that's so evocative. So thank you again. And
thank you.
Stay tuned to our newsletter coming up next semester. We have a book club coming up. We're going to look at color of bricks and clay for members. We have other talk and I'm just forgetting the speaker, on fashion upcycling and using color in February. And we will let you know our March speaker once we get those details all sorted. So stay tuned to our website, follow us on Instagram, and there are lots of other color organizations that show talks too. So they're all connected through the AIC. All right. Thank you, everybody. Nice to see everyone. And have a good evening.
Thank you very much.
Bye-bye.
Bye-bye.